Welcome back to The Explainer. I am so incredibly pumped, pun absolutely intended, for our topic today. We're looking at some absolute engineering marvels from the ancient world, specifically focusing on how two monumental, completely brilliant mechanical inventions mastered the movement of water. You know, if you've ever found yourself wondering how ancient civilizations managed to pull off these massive, mind-boggling feats of hydraulic engineering, you are definitely in the right place. Let's get into it. All right, really quickly, here is our roadmap for today. We're going to cover 1. Conquering water and gravity, 2. The Archimedes screw, 3. Ctesibius and the force pump, 4. Building the ancient mechanics, and 5. Ancient tech in the modern world. So I really want you to hold this central question in your mind as we go through this today. How on earth did ancient empires move literally millions of gallons of water without a single drop of gasoline or electricity? I mean, think about it. It's a logistical nightmare. Entire empires would literally live or die based entirely on their ability to solve this exact problem, and they had to do it on a monumental scale. Section 1. Conquering water and gravity. Okay, so moving water upward is the ultimate physical limitation. It's the big boss battle of ancient engineering, because without conquering this hurdle, you can't irrigate your crops in the dry seasons, you definitely can't keep your deep mines from flooding, and you absolutely cannot sustain these massive, densely populated cities. Gravity is just relentlessly pulling water down to the lowest possible point. So to build a thriving civilization, ancient engineers had to figure out a way to consistently and reliably push it back up. Moving to Section 2. The Archimedes screw. Now, what's super fascinating about this device is its debated history. It's like a giant historical puzzle. I mean, it's famously named after Archimedes of Syracuse, who gets the credit for inventing it while visiting Egypt back in the 3rd century BC. But the timeline might actually stretch way further back than that. Assyrianologist Stephanie Daly actually proposed that bronze water screws were potentially used centuries earlier. We're talking the 7th century BC by King Sennacherib to water the legendary Hanging Gardens of Babylon. No way, right? But regardless of exactly where it started, the idea spread like wildfire across the Roman Empire, and it even saw this massive revival during the Dutch Golden Age, where they used them with windmills to literally drain entire landscapes. Now, looking at the design, there are actually 4 main variations of this ingenious machine. You've got your spiral screws, which wrap small closed tubes around a larger central one. Then there are trough screws, where the blades rotate inside a stationary U-shaped trough. You have tube screws that are completely enclosed in a cylinder. And finally, casing tube screws, where the entire outer shell and the internal blades all rotate together as one solid piece. But here's an interesting takeaway for you. Modern manufacturers actually steer clear of the casing tube and closed spiral designs today. Why? Because they have pretty terrible ventilation and they tend to trap air. It just goes to show you how we've been tweaking and refining this tech over millennia. But hey, don't let the ancient origins fool you for a second. This is a highly mathematical device. You can't just take some twisted wood, throw it in a river, and cross your fingers. Designing a screw that's actually efficient requires calculating some very specific external parameters. Things like the outer diameter, the total length, and the exact angle of inclination. And then you have to perfectly balance the internal parameters to match: the inner radius, the exact number of helical blades, and the pitch of the screw. It is an absolutely stunning display of mechanical geometry, all perfectly calculated to maximize the exact volume of water scooped up with every single rotation. All right, Section 3, Ctesibius and the force pump. Enter Ctesibius of Alexandria. This guy was an absolute pioneer when it came to compressed air and hydraulics. And the real game changer here, his ultimate innovation, was the check valve. Think about it. Without check valves, a moving piston is just sloshing water back and forth in useless circles, right? By creating a simple flap or a ball that opens up when pressure pushes from below, but then snaps tightly shut to block the water from flowing backward, Ctesibius made the whole concept of a pressurized, double-acting piston pump actually possible. Let's try to mentally visualize how this works. It's pretty brilliant. You have 2 cylinders, and they're working in exact opposition on a rocking beam. So, in step 1, piston A pushes down on its delivery stroke, and that forces water out through its top check valve. At the exact same time, in step 2, piston B is pulling up on its suction stroke, which draws fresh water in through its bottom check valve. Then in step 3, they completely swap roles. Because they're always alternating like this, the outlet pipe is receiving water on every single half stroke. That push and pull cycle creates a near continuous, highly pressurized stream of water. And seeing them side by side like this brilliantly illustrates the divergence in ancient engineering. I mean, look at how perfectly these machines complement each other. The Archimedes screw? It uses rotary motion to move massive volumes of dirty, debris-filled water, but over a very low incline. Chrysippus's pump, on the other hand, uses reciprocating motion to blast clean water at incredibly high pressures for high vertical lifts. It's two entirely different mechanical approaches, specifically engineered to solve two completely different liquid transport needs. Section 4. Building the ancient mechanics. Let's see how they actually made these things. I want you to just imagine fabricating a high-precision pump using only ancient hand tools. It's wild. First, they'd cast the cylinder barrels from bronze, which was typically a mix of 88% copper and 12% tin to resist rust and corrosion. Next, they had to turn the pistons by hand, so they fit inside the cylinder with a microscopic 0.5 millimeter clearance. But wait, metal scraping on metal is going to leak, right? To solve this, they machined a little groove into the piston and packed it tightly with vegetable-tanned leather that had been soaked in olive oil. The oils swelled the leather up, creating a perfect pressure-tight seal against the bronze wall. Finally, they meticulously ground the bronze check valves flat using an abrasive paste until absolutely no light could pass through them, which guaranteed a watertight seal. Now, all that insane precision matters because of one specific number, 10.3. 10.3 meters is the absolute maximum theoretical limit you can physically suck water upwards using any piston pump. It's literally bound by the physical laws of atmospheric pressure pushing down on the water source. So in ancient practice, dealing with minor inevitable leaks, they could reliably pull water up about 5 to 6 meters. But what about the output? Well, here's another number for you, 10. That is the number of liters per minute that an ancient Roman bronze pump could blast out. We actually know this because one was excavated perfectly intact from the ashes of Pompeii. Because it could provide this continuous, highly pressurized jet of water, this pump became a primary weapon of the Roman fire brigades, the Vigilus, and it's basically what kept those densely packed ancient cities from just burning to the ground on a regular basis. Which brings us to our final section, Section 5. Ancient Tech, Modern World. You'd be amazed at the incredibly varied modern footprint of the Archimedes screw today. Because it can effortlessly handle dirty water and large solids without jamming up, it's heavily relied upon in modern wastewater treatment plants. And because those turning blades are actually quite gentle, we use them as reverse micro-hydroturbines that are completely safe for fish to swim right through. Believe it or not, there's one powering Windsor Castle right now. They're used in fish hatcheries, they power the flow of those amazing chocolate fountains, and get this, a highly specialized earth-removing screw was even used back in 2001 to carefully extract subsoil and stabilize the Leaning Tower of Pisa. Meanwhile, the legacy of Chrysippus is all about power and pressure. That ancient bronze fire pump pulled from the ashes of Pompeii, it is the direct mechanical ancestor of the complex systems operating quietly inside your car right now. The high-pressure fluid dynamics of your power steering, the incredible lifting strength of hydraulic floor jacks, the absolute precision blast of diesel fuel injectors, they all trace their mechanical lineage straight back to that double-acting piston and those clever little check valves engineered in the Mausoleum of Alexandria over 2,000 years ago. Which leaves us with this final thought. We rely so heavily on electricity and complex computers today for everything, but seeing how fish-friendly screw turbines can generate clean micro-hydropower and seeing how effectively these manual force pumps can move water without needing a single drop of gasoline, I just have to ask, what modern sustainability crises could we solve tomorrow simply by looking backward at the highly efficient, low-impact mechanics of the ancient world? Really think about that the next time you turn on a tap. Thank you so much for joining me on this explainer, and I'll catch you next time.